Hello, here's another introductory episode. This time we are going to talk about the generator. The task for the generator is to convert models, to transform one model into another. So for example, if you've got a robot script, you can have it converted into Java, and the Java code can then be run. Or if you've got Java extended with certain extensions like parallel for loop, for example, parallel for loop can be generated into Java without parallel for loop, that then can be compiled by the Java compiler. So this is the generated code. There's no parallel for loop in it any longer, but the semantics of this code is identical to what you expect from a parallel for loop. So it will loop through the body in parallel, going through all the numbers in the collection of numbers. A decision table like this one will be converted into a set of nested if statements. And a money literal like this one will be converted into an instantiation of a new money class. To refresh your memory, the ultimate target of code generation in MPS is typically a textual language like Java. The textual representation is created in the text generation phase when a language that forms the base for certain family of languages is converted, is flushed into a textual buffer. So this is the final phase called text generator, which can be customized through the text gen aspect, but this has nothing in common with the generator. The task for the generator is to do model-to-model transformations that ultimately lead to some bottom line projection language, which then can be text generated. So in this presentation, we'll be focusing on the generator, on model-to-model transformations. The text gen aspect will be covered by one of the next episodes. So when we talk about the generator, we don't talk about generating text, but we talk about transforming models into turning an AST into another AST. As an example, let's look at the money literal. So at the beginning, we have this piece of code. Here we have 10 euro, which is not valid Java construct. It is an instance of money literal concept, which is an expression, refers to some currency, and contains an amount. So in order to be able to generate valid Java from this, we first need to replace 10 euro with something valid. If we preview what gets generated, we need to replace it with instantiation of the money class and give it the right parameters, 10 and euro in our case. So this is the task for the generator. Once we have this, now once we have base language code like this, then the text generation phase can easily transform this into text Java. But before doing that, we need to convert the model, change the AST. So what the generator does, it goes through the model and looks for all nodes that can be reduced, that can be converted into something that's sort of closer to the bottom line language, base language, or Java in our case. So it discovers all money literals and replaces them. And then it would discover all decision tables and replace them, and all parallel loops and replace them. And this would be done in distinct phases. You can observe the generation process if you turn on the transient modes here. So once you turn this on, if you run the generator will leave a trace here at the bottom. You'll get all the steps that the generator went through. So you'll see how your code in the model was transformed from the original form, like this one, gradually into the final form where our money literal is converted, completely removed. you may check out the generation plan, the strategy that the generator chose for generating your model. If you click on the model and pick Show Generation Plan, you get an outline of all the phases that the generator plans to go through, and with all the languages that will be transformed in that phase. So in our case, for the sample of all Java extensions, we see that in the first phase the parallel for loop will be replaced. And then we'll do collections in 2 steps, then closures, then the constant sample, decision table, if and unless, and money is done in the 9th phase. So if we look back into the transient models, then we should see in the 9th phase, somewhere around here, the money literal should be removed. So it is removed here. It's removed in the 9th phase, but it's not removed in the 8th phase. So 9th phase is the phase when the money literal is being converted. While if I remember correctly, in the first phase the parallel for loop is being removed. So if we go to the parallel example, which is this one, we see parallel for, and after the first transformation, the parallel for is gone. Right, so that was the first phase that the generator did. The conversion is defined through templates. So for our money literal, when we need to replace the literal, say that says stuff like 10 space euro, we want to convert this into new money, and then 2 parameters. One is the amount and the second one is the currency. So to define this rule, the money literal has a generator defined. Let's look at the aspects as they are defined. So this is the language that defines money literal, and it has several aspects. We already know about most of them. In this episode we focus on the generator. Unlike the others, generator is a module, it's not a plain model, so it contains models underneath. So in our case there are 2 models, one is a generator model, one is a utility model, so this is a plain model containing a helper class. So if you want to refactor your generator into reusable classes, you can do so through creating more models inside the generator. On the generator module, you can define similar properties to the properties you can define on languages and solutions, which are also modules. So you can define its dependencies and the languages that you can use inside the generator. Additionally, you can define priorities, so you can specify that a particular generator can only run after another generator. So in our case here, we define that the money generator has to be run earlier or at the same phase with a base language generator and closures and a few others, because we want to be sure that the code that we generate out of this still will be processed by the other generators, because we not necessarily need to target the ultimate bottom line base language, but we might target a collection language, for example. But the collection language still cannot be transformed into plain textual Java, so we need to make sure the generator for collections language is run afterwards, not earlier than our generator for money. Well, in generator models, you can create generator-specific root concepts like mapping configuration, mapping scripts, template declarations, and template switches. Mapping configuration is the directory which specifies all the rules that should be applied when transforming your language into other languages. So typically you define reduction rules where you define how individual concepts should be translated. For our money literal, we define a rule, reduce money literal. So if we go to the definition, here we see the template that will be used to transform a money literal like this into a Java class like this. The template is based around the target code. In the target language, we define a piece of code that will be generated out of our money literal, and then we customize it with macros. And for each macro, we have to open the inspector. In the inspector, we see the details. So the first macro is equal to node amount. So it will take the amount from the input node, and node in our case is money literal. So it takes the money literal, takes its amount, and will replace the property of the integer constant, the property value, with the property amount of the money literal. Well, and here the second parameter, so it is a string literal, and the value of string literal will be replaced through a property macro with the name of the currency. You know, node.unit, that's a currency unit. Currency unit has a name because it's an I-named concept. So we'll get the money literal inserted into the string literal. Now, and the whole thing is then wrapped with template fragment, meaning that, you know, this is the thing that will replace the 10 euro literal in the model. So in the AST, this selected piece of code will be removed from the AST, and instead this piece of AST will be placed there. Bear in mind, this is not textual transformation, right? We're putting in a piece of AST. So the AST that we build here and mark with template fragment will be taken out from this code. So it will be removed from this block statement. It will be taken out and put in the model instead of this. And this is the way the generator gradually simplifies the model and removes all the concepts for which reduction rules are defined. Let's pick another example. A repeat command in the robot Kara language. The semantics of this command is to repeat 3 times the body, whatever is in the body. If we go to the command, in the generator for the robot language, in the mapping configuration, there's a set of reduction rules, one of which specifies how a repeat statement, how a repeat command should be reduced. Since we need to generate valid Java out of the robot language, we need to target Java. So a repeat statement could be easily modeled by a for loop in Java. So that's why in the template we specify a for loop. And we'll do it from scratch here. So this is an empty template. In a template we need to specify the node from which we start. We might start with a for statement. And this whole for statement will be a template. So now we have a template fragment containing a for loop. We'll start with an integer with a value 0. Now we'll continue until I is smaller than 10, and we'll increment I along the way. And we'll print system out print line, whatever. This is a sample code in the target language that is very close to what we want to generate. We just need to parameterize it with the value from the input model, from the repeat command. So the repeat command itself, it specifies how many times we want to iterate, and the body, the list of commands that we want to iterate over. So the upper boundary of the for loop can be customized through a property macro, node.count. So now instead of iterating all the way up to 10, we change this integer constant value to node.count. So it will 3 in our case. So now we'll be iterating 3 times. And instead of printing out foo, we'll replace the whole statement with a list of statements that will be contained in the body. So now all the commands in the body of the repeat statement will replace this system out print line. So now we define that instead of a repeat command that's somewhere in the AST, we want to place a Java for loop that will iterate from 0 to whatever the repeat statement had in count, and we want to replace this useless body with the actual body of the repeat command. And now this copy source macro ensures that these commands are not inserted as they are, but they are also reduced to whatever they define to be reduced to, because step is not a valid Java command. It itself needs to be reduced into some sort of Java code. Okay, nice. But how does this whole thing start? You know, there's the topmost robot Karel language element, script, which needs to be transformed as well. So how does the whole generation start? How does a script get translated into a Java class? A Java class with the same name, maze, as that was the name of the script, and now containing all the commands somehow generated into Java. So let's look at the generator for the robot Karel language. So the generator contains the mapping configuration, and in the mapping configuration, on top of reduction rules that we know already, there are also root mapping rules, and these apply to root concepts. Script is a root concept. So this rule applies to the script. So whenever there's a script, it will be replaced with a map script. When you specify a root mapping rule, you create a new root, you define a new root template, and you have to pick from the imported languages the root concept that you want to choose. Well, since we imported base language only, we can pick whether we want to generate a class, enum interface, or add interface. If we imported, for example, the constants language, now we could pick constants instead and generate constants, for example. Okay, so let's get back to how it was before. So in our case, we need to generate a Java class, and the template in the sample looks like this. So this is a Java class, a template for a Java class. So again, a piece of AST, a piece of model. Mind you, this is not plain Java. This is base language, projectional version, where you could use projectional extensions like decision tables, for example. So if it made any sense, we could create a decision table here and generate a decision table. We don't have to generate plain base language. We can generate more advanced, more higher level languages if we need to. So now here is a template, the template for a Java class, and again it's customized with values from the input model. So here we, for example, specify the name of the class that will be generated. It should be the name of the original script. Node is the script. It has a name, but just to be sure, we replace all spaces with non-space characters to ensure this is a valid Java identifier. So we customize the name of the class, and then we use certain macros to customize the code. We've got a public static void main method that remains as it is, but we alter certain commands. So this Java class then, in its perform method, Now the body of the perform method will not contain the system out print line, but instead, thanks to this loop macro, it will go through the body of the script, through all the commands, and for each of the commands, it will replace the system out print line with the actual command. So now in this perform method, we will see all the commands listed as statements, but not the commands as they are, so we won't see the stuff like find door, step, and sniff around, because these are robot language specific commands. This would not be valid statements in Java. So the copy source macro ensures that the current command gets first translated into Java and only then inserted into this Java method. And the translation, as you expect, is defined in the reduction rules in the mapping configuration. So for each command, so if a step command is found, for example, then for step there is a reduction rule defined here. So this piece of code will be taken because it's marked with template fragment. So this piece of code, this AST, is taken out from here and inserted into here for the step command. And then the next command is taken, and again a reduction rule is found here for left turn, for example. And whatever Java code corresponds to the left turn is taken out from here and inserted here below the previous command. So you've seen several macros already. There's property macro that allows you to change properties of the marked elements. In our case, we change the name of the class, or we could change the value of a string literal, for example. Then there are node macros that you attach to nodes, like this loop is attached to a node. You know, this is node. This is a node in the AST. This is a statement, and the loop is attached to it and will iterate over a collection of commands, and for each of them it will insert the node. But because the node is also annotated with copy source will replace this node with whatever is specified in here. In our case, it's the command. But along the way, it will also invoke reduction rules for that command. So the command is not inserted as is, but only after reduction into something else. And there are more types of node macros. You know, there's a whole bunch of them. I recommend you go through the documentation and through the generator tutorial to get familiar with those macros. Okay, back to mapping configuration. You see there are a lot of options that you can customize here. Root mapping rules and reduction rules are those that we've covered already. There are a few that we haven't yet, but again, if you go through the documentation and tutorial, you'll understand what these mean. But there's one part that I want to talk about in this tutorial before we finish, and that's called mapping labels, because it is an essential part of even very trivial generators. For the robot language, we utilize mapping labels when we define routine definitions, like find door, for example, and calls to these, like here, where we call the definition. So we've got a definition of some sort somewhere in the model, in the AST, either in the same tree or in another tree, on another root. And then we've got calls or references that point to the definition. Right? So if you change name or anything in the definition, the reference reflects that. And during generation, you need to translate this into a Java method. And you need to change this into a method call. And that method call needs to call the right method. So you need to turn this into a Java method call that calls a method that was generated out of this definition. And mapping labels are a tool to give you this. A mapping label essentially is like a map or directory. It maps from routine definitions to instance method declarations. So it's a map that for a definition like this one gives you a Java method that was generated out of this. So in the mapping configuration, you define the map itself. It's empty, but it is defined and has a name through which you can refer to it. And then when you reduce a routine definition, so now when reducing this guy, you create a public void method. You customize that method, you give it a certain name. Again, here we kind of take care of spaces in names. We also distinguish local routines and routines from a library, but that doesn't really matter here. We just somehow generate a name from the routine definition. So notice if we change the name, it would be even more difficult for the Java method call to find the right method definition to call, because the name is not identical to find_all. Or if there was a space in the name, right? Now, what is the name now? The name could be anything. You can't know that. So you can't rely on the fact that you might remember the name of the original definition. The name of the generated Java method might be very different. So here we generate the method, and now we add a node macro, in this time label. And in label we specify a mapping label that should store the generated Java method. Many macros allow you to do that. In many generator macros you can specify the mapping label so that the macros will then take the node, the original node from which the routine definition, the input node, they will use it as a key, and then the generated Java method as a value and insert it into this mapping label. So now after this reduction rule is called, the routine's mapping label will contain a mapping between this routine definition it was used as an input and the generated Java method that was generated out of it. So we have it there. And then, when a routine call is being reduced, so this guy, find_all, then it will use that dictionary to find out the definition. It will find the right method there. And it will utilize a reference macro for this. Perhaps I should give a little bit more explanation here to why this template is so complex. So here we define a class. The class doesn't really need a constructor, but it has a method bar which serves as a placeholder, and then has a method buzz, and in that method buzz we call bar. So we do all this so that we get a local method call here. So now we can have a local method call which calls this bar. And all we have to do now, we just replace with the reference macro the local method call, the method that this local method call points to, so that it no longer points to this bar here, but it points to the method that was generated from our routine definition. So we only added the class and this method to have valid AST, so that this local method call is valid. But then with reference macro we make this method call bar to point to this method, and this whole thing can be thrown away. The only part we need here is this call, this. Because this is annotated with template fragment, so only this part during generation, this will be cut out from this piece of code, the rest will be thrown away, and this piece will be inserted into the AST where a routine is being called. So it will be inserted instead of this guy. So this find_all will be gone, and instead we'll add a local method call, this one. But along the way we'll change it so that the method call no longer points to this bar method, which is being deleted anyway, but instead it will point to the routine definition method, to this method. And it is done through the code down here in the inspector. So in the inspector we specify, we take the generator context and ask the generator context for the routines mapping label for this guy. So now we get the dictionary, and in that dictionary we search for the value for this key. Now node is the routine call, right? Node is this find_all, and find_all points to this definition find_all. So this is what we do here. We take the find door definition, go to the routines map, and search for the value, so for the method that was generated out of this definition. We get it, and the reference macro will replace it here in the method call. So now this method will call the right Java method here. And that's it. The generator context object is very useful. It can give you access to various elements of the generator. Typically, you will use it to get stuff from mapping labels like we get here. But you might also get hold of the input and output and original models. You might get hold of various properties of the generator. You might indicate errors during generation or warnings. You might store stuff in the generation session for later retrieval. Or you might also generate unique names, which is pretty useful for variable declarations. So we might go to the repeat statement generator, and here the local variable, we could change the name to be a unique name. So now we'll generate a unique name, and we'll start with whatever you like as the base. So we take foo, and this will be globally unique name. Or we might be more specific. We might indicate that the name needs to be unique only within, let's say, the surrounding script. Now within the Java class that's generated from the script, all these variables for different repeat statements will all have different names, and so there will be no name clashes between them. When defining reduction rule, you create an empty one. You provide a concept for which you are defining a reduction rule. You might specify whether it also includes inheritors or not, so sub-concepts of this concept. You might specify a condition, so a Boolean function that says true or false for individual nodes, whether the reduction rule is applicable or not. For example. Well, and now you have to choose the consequence. Now, several options. Alt-Enter is always handy, and you hit New Template. And this way, a new template is created. You can navigate to it and define it. Or you can pick, with Control Space, you can pick one of the already defined templates. Or you might create one inline. So inline template, so instead of creating a separate template for some simple cases, you can just define the template in here. So now we could, for example, generate this into a single line comment, for example. Single line comment. So this stuff will be generated wherever step shows up. Or we might create a template with context. So now first we create some sort of context. Let's say class concept, and now within here we might create public static void main method, and here we'll create a comment, and only this comment we want to be part of the generated code. So we'll mark it as template fragment. We might parameterize it if we wanted to. Let's say we would like to parameterize this with node dot whatever, some string. So now this template fragment has a context, so just like for our, if you remember, the routine call needed a context. So similarly, you can create context right here within mapping configuration. Then a few other options. You could pick abandon input. Say it will just forget about step and not include it in output in any way. Or you could inline a switch. So switches in the generator allow you to decide what to do under certain conditions, under certain types of nodes. So we could have a default case when single line comment will be generated, and then we could have different cases So if this, for example, was a repeat command instead, then we could, for case when node count is equals 0, we could abandon the input. For case when node.count is less than 0, we could have an inline template. Again, single line comment. And in property macro, we could just generate a context, report an error. And for node.count bigger than 0, well, we could then call this reduce repeat that we have already defined. So this would be a generator switch, reacting differently to different cases. So you see, the generator gives you a lot of various options. I recommend you check out the user guide. In the generator section you might find more about the generator itself, some quick tips on the generator, and then you should definitely check out the generator demos tutorial. So in several steps it will give you an insight into the many options that the MPS generator gives you when transforming models in MPS. That was quite a ride, wasn't it? Thanks for watching. Goodbye.